So folks, I think the most important thing in our pre-work to get ready for is how to construct these tree diagrams. And we'll worry about the explicit computations of some of these chain rules in later in our in-class work. So what I'd like to do first of all is let's go ahead and create a tree diagram for this sequence of, or this large function z here, which is a function of x and y. But we're going to consider x to be a function of s and t, and y to be a function of just the variable s. So there's a lot of interrelationships happening between these variables, so let's go ahead and clarify them by sketching our tree diagram as we did in the previous example. So let's go ahead and label the output variable z, and z is initially we think of it as being dependent upon x and y, so as far as z is concerned, x and y are the independent variables. But we know that x is a function of s and t, so x itself is dependent upon the variables s and t, and y we're told is a function of s. Okay. What I'd like to do now is let's go ahead and fill in our derivative notation here, because something interesting is going to happen. If I want to think about this leg of computing the chain rule for something, I'm going to call that leg the partial z partial x leg of that. Whereas this is going to be what? This will be the partial z partial y leg. Okay. So what would these two legs be down here? Well, this would be the partial x partial s leg, and this would be the partial x partial t leg. Now my purpose for doing this example actually wasn't for any of these pieces right here, but this last piece right here. Notice that y is a function of how many variables? Y is a function of just the independent variable s. So when I go to talk about y's derivative, we're talking about how does y change as the single independent variable s change. And so very important, folks, I'm going to use the one variable notation for the derivative dy ds. So now I've sketched this tree diagram. I think we're ready to go ahead and explicitly give formulas for partial z partial s and partial z partial t. So partial z partial s would be equal to, and then remember what we did before, folks? We're going to trace all of the different routes that can get us down to the independent variable s. So here we go. This is going to be partial z partial x, and we're going to multiply that to partial x partial s. Well, that's for that orange route there, but how else could we trace down to the independent variable s? We could go this route. And so if we tackle that, and remember we sum these rates. Rates are additive, so we're going to sum these rates. So we will take partial z partial y, and we're going to multiply that to the derivative of y with respect to the variable s. So one of the reasons why I did this example here, besides just to give you another example of a tree diagram, was because notice here I'm using the single variable derivative as opposed to over here where I'm using the partial derivative. Why is that? Because as far as x is concerned, it's a multivariable function. It depends on two different inputs, s and t. As far as y is concerned, it's a function depending upon the single independent variable s. So if we go ahead and compute partial z partial t, in this case, if we go to trace the routes down there, notice there is only one route that I can take to get me to that independent variable t there. So that's going to be equal to partial z partial x, and we're just going to multiply that by partial x partial t, and that was the only route that would get me to that independent variable. And so there we have these two very different looking chain rules depending on which of the independent variable we're working with. Folks, I hope this helps. We'll pick it up in the next example.